Like, subscribe, and hype the video. Also, leave a comment on any topics you want to hear about in the future. Okay, let's dive in. In September of 2022, NASA did something that, until that exact moment, had only ever happened in disaster movies. They deliberately crashed a spacecraft into an asteroid on purpose at 14,000 miles per hour, just to see if humanity could actually change the path of a moving space rock. The mission was called DART, and by the time you finish this video, you're going to understand exactly how it worked, what the real results were, and why, almost immediately after it succeeded, a wave of conspiracy theories started circling around it that we're going to dig into in the very next episode. Some of those claims get genuinely strange, so make sure you stick around for that one too. But first, let's understand what DART actually was, because the real story is honestly wild enough on its own. To understand why DART mattered, you first have to understand the actual risk it was built to address. Scientists track a category of objects called near-Earth objects, asteroids and comets, whose orbits bring them within roughly 30 million miles of Earth's own orbit. Tens of thousands of these objects have been identified and cataloged, and more are discovered every single year using dedicated survey telescopes that scan the sky nightly. Most of these objects are small and harmless, but a portion of them are large enough and pass close enough to be classified as potentially hazardous, meaning that, over a long enough timeline, their orbit could eventually intersect with Earth's own path around the Sun. The actual risk is statistically low on any given year. An asteroid large enough to cause serious global consequences strikes Earth, on average, only once every several 100,000 years. But rare doesn't mean impossible. And for decades, scientists had a real, unanswered question hanging over the entire field of planetary defense. If we ever did detect a dangerous asteroid heading our way, with enough advance warning, would we actually be able to do anything about it? Up until 2022, that question had never been tested in real life. It had only existed in computer models, simulations, and theoretical physics papers. DART was designed to finally find out for real. Like, subscribe, and hype the video, and let's get into exactly how they pulled this off. NASA needed a target that was safe to test on, but realistic enough to prove the concept actually worked. They chose a pair of asteroids, a larger asteroid called Didymos, roughly half a mile across, and a much smaller asteroid orbiting around it called Dimorphos, roughly the size of a football stadium, about 525 feet across. Crucially, neither of these asteroids posed any threat to Earth before, during, or after the mission. Dimorphos orbits Didymos every 11 hours and 55 minutes, and that orbital period turned out to be the key to the entire experiment. Because Dimorphos is a moonlet orbiting a larger object rather than the Sun directly, scientists on Earth could precisely measure any change to its orbital period around Didymos using ground-based telescopes, without needing a spacecraft to fly back out and check in person. In other words, this pair of asteroids functioned almost like a controlled laboratory experiment, conveniently parked tens of millions of miles away in space. Small enough to actually move, safe enough to test on, and measurable enough that scientists could prove, with real data, whether anything had actually changed. The DART spacecraft itself was surprisingly modest, roughly the size of a small vending machine, weighing about 1,210 pounds at launch, with two long solar panel arrays extending outward to power its systems during the 10-month journey to its target. It launched on November 24, 2021, atop a SpaceX Falcon 9 rocket from Vandenberg Space Force Base in California, and spent the following months traveling toward the Didymos system, using an onboard camera and an autonomous targeting system called SmartNav to identify and lock onto Dimorphos during the final critical hours of approach. A process that had to happen with almost no help from mission control on Earth, since the roughly 38-second communication delay at that distance made real-time human steering completely impossible during final approach. By the time DART reached its target, the spacecraft was flying without any human able to manually correct its course in real time. The entire final impact sequence depended on the spacecraft's own onboard systems recognizing Dimorphos, locking on and guiding itself directly into the asteroid, completely autonomously. Like, subscribe and hype the video, because what happened next is the part that made history. On September 26, 2022, at roughly 7:14 p.m. Eastern Time, DART slammed directly into Dimorphos at approximately 14,000 miles per hour. The spacecraft's own camera transmitted images back to Earth in the final seconds before impact, showing the asteroid's rocky, rubble-covered surface growing rapidly larger in frame, right up until the signal cut out completely, the moment of impact itself. A separate small satellite called Lysicube, built by the Italian Space Agency and released from DART about 2 weeks before impact, flew past the collision site minutes later and captured images of the resulting debris plume, a massive cloud of rock and dust ejected outward from the impact site, confirming visually that the collision had been a direct, successful hit. But a direct hit alone wasn't the actual goal of the mission. The real question was still unanswered in that exact moment. Had the impact actually changed the asteroid's orbit at all? And by how much? Over the following weeks, observatories on Earth tracked Dimorphos's orbit around Didymos using telescopes around the world, carefully measuring its new orbital period and comparing it against pre-impact data. The result: Dimorphos's orbit around Didymos had shortened by approximately 32 minutes, going from 11 hours and 55 minutes down to roughly 11 hours and 23 minutes. NASA officials called this result far beyond their minimum expectations. Mission planners had originally defined success as shifting the orbit by just 73 seconds or more. A 32-minute change represented a result roughly 25 times larger than what they considered the minimum bar for proving the concept. Scientists later determined that part of the reason the shift was so much larger than predicted came down to the physics of the impact itself. The collision didn't just transfer momentum directly from the spacecraft. It also ejected a substantial amount of rock and debris from Dimorphos's surface in the opposite direction of DART's approach, and that ejected material acted like a secondary rocket thrust, amplifying the overall change to the asteroid's momentum well beyond what a simple debris-free collision would have produced alone. For the first time in human history, we had real, measured, repeatable proof. If we detect a dangerous asteroid heading toward Earth with enough advance warning, we now have tested, working evidence that we could actually do something about it. So that's the real story of DART, a vending machine-sized spacecraft, flying autonomously for 10 months, successfully striking a target the size of a football stadium millions of miles from Earth, and proving for the first real time in human history that planetary defense isn't just theoretical anymore. But almost as soon as the mission succeeded, a strange thing happened. Conspiracy theories started spreading almost immediately. Claims that DART wasn't really a planetary defense test at all, that it may have actually been cover for testing offensive space weapons technology, and even claims questioning whether the entire impact and its supposedly enormous orbital shift had been exaggerated or fabricated altogether. In the next episode, we're going straight into those theories, what people are actually claiming, why some of these claims picked up real traction online, and what the documented evidence actually says about each one. Some of what we found while researching this might genuinely surprise you. Like, subscribe, and hype the video so you don't miss part 2. And let me know in the comments if you'd already heard any of these dark conspiracy theories before today. I'll see you in the next one.